Welcome back, everybody. So in our last video, we talked about integration using U substitution, and we did several examples, and we saw, the theory behind how all that works. That what substitution is really doing is doing an integral by undoing the chain rule. That's the most important thing to remember when you're doing one of these. That the U is really the stuff we would have if we had a chain rule and we had to take the derivative of a function that had a bunch of stuff in it. It wasn't just a function of x. So what we need now, I think, is many more examples. So here we go. Here's an integral of e raised to some power with stuff, right? With bunches of x's there. This being multiplied by 2x squared and then dx. So when you see something like this, your first thought is, well, first thought right now may be run away and hide because this looks terrible. But you'll see this is really not bad at all. But what's going on in this problem is I have e raised to some awful looking power, and this being multiplied by 2x squared dx. Okay? Now again, the 2 doesn't really matter because I can always slide numbers in and out of the integral. The x squared, though, is really important because that x squared looks suspiciously like something that came from the derivative of the stuff in the exponent of the e. In other words, I've got e raised to the 4x cubed plus 7, right? So e raised to that stuff. The derivative of all that stuff would be, 4 times 3 makes 12, x to the second power plus 0. So the derivative of that stuff in the exponent of the e is 12x squared. And again, the numbers don't really matter. The constants I can fix. But the derivative there has an x squared in it. And sure enough, sitting out beside that e is a wonderful x squared. Right? So this thing looks like it's been chain ruled. Right? That the derivative of the stuff will have an x squared in it. And sure enough, there's an x squared sitting out there being multiplied by the original exponential function. So this is perfect for doing U substitution. But here's what we're going to do. I'm going to let U equal all that stuff, the 4x cubed plus 7. And just like we said, when we take the derivative of that, the derivative of 4x squared plus 7 will be 12x squared. So if U is 4x squared plus 7, du would be that derivative, 12x squared dx. Okay, so what do we do here, right? Again, in the last video, we talked about several ways of putting in the constant that we need and then dividing by the constant outside. What we could also do if we wanted to do that is to try to use this equation to solve for what we have. In other words, there's 2x squareds, right? And on the right-hand side of my equation there, I have 12x squared dx. So if I left 2, right, and just divided a 6 on the other side, then what you get is 1/6 du is 2x squared dx. And that lets me substitute in 1/6 du in place of 2x squared dx. Now, if you don't like thinking about it that way, you could go through this procedure and solve completely for dx. You could say that dx is 1 over 12x squared du, and then plug that into the integral in place of dx. So I would end up with e to the 4x cubed plus 7 times the 2x squared, and then I could replace that dx with 1 over 12x squared du. Then the x squareds will cancel, the 2 and the 12 cancels, and end up with that 1/6. Okay? So either way of doing that is perfectly fine. And in the last video, we talked about ways of just ignoring that original 2 completely, putting in a 12 inside and a 1/12 outside. You could do that too. And you would still end up with a 1/6 and an e to the u. Okay? So this is probably the easiest integral ever, because the integral of e to the u is, of course, just e to the u. Right? All we have to do is make sure that we leave the 1/6 outside still there, and that we don't forget the plus c. And now, last step, and again, you don't want to make this mistake, right, on a test, is go through and do all the hard work and forget the very last step, which is returning our answer to something with x's in it. The original problem was full of x's, so we want our answer to be full of x's, not u's. So instead of 1/6 e to the u plus c, we want 1/6 e to the whatever u was, which was, in this case, that was 4x cubed plus 7, and then plus our c. Okay, let's try something with some trig. So here's a secant squared of 3x minus 1. Okay, well, okay, so you see this for the first time, you go, oh gosh, this looks awful. Wow, well, as a secant squared, I know that a secant squared is the derivative of a tangent. So if I were investigating a differentiation and I came upon a secant squared, I'd go, I know what happened to you. You used to be a tangent. You've been differentiated. Now you've been turned into a secant squared. But we have to be a little careful because that works, right? If it's the derivative of tangent of u, then its derivative would be secant squared of u. But here I don't, or I could say the derivative of tangent of x would be secant squared of x, right? As long as it was one variable inside with no extra, multiplying and subtracting or whatever happening to it. But in this example, I've got secant squared not just of a single letter, but of 3x minus 1. See, that's a problem. What I'm going to need to do is treat that as secant squared of a bunch of stuff. Now, what's the derivative of that stuff? Oh, well, it's just 3. So that's easy, right? I don't have to worry about any x's or anything outside. This will just go completely straightforward, right? I'll let u be that stuff inside the secant squared. Then if u is equal to 3x minus 1, take the derivative, du would be just 3 dx. And I could solve for the dx, right, and turn that into 1/3 du. Now I just plug that back in, and I get secant squared of 3x minus 1 dx becomes secant squared of u. That's just substituting in my stuff. The dx turns into 1/3 du. That's perfect. I can take that 1/3, drag it outside the integral, so it's out of my way, and that leaves me with a third. And then the important thing is an integral of secant squared of u, du. And how do you integrate a secant squared? It becomes a tangent. So I get 1/3 tangent of u, and again, the final step is just to make sure that I have an answer that has x's in it, not u's, because my problem started with x's. So I'll go back and turn that u into 3x minus 1. Okay. So what if I had something a little more complicated? What if I did something like this? So here's a secant squared again, right? Secant squared of x, but it's being multiplied by, a big ugly parentheses, like a tangent of x plus 3 in the parentheses, and then that's being raised to the 4th power. So I'm looking at this scene of this awful differentiation. Right? How do I piece this back together? Well, do I see something and its derivative? Right? Do I see some stuff and its derivative? I do. The derivative of a tangent is a secant squared. So that tangent on the inside of the parentheses starts to look a whole lot like that ought to be my stuff, and then its derivative will be the secant squared outside. But I don't want to let u just be the tangent, right? Because that would leave me with, if I did that, u plus 3 inside the parentheses. And that's not great either, because then how am I going to integrate u plus 3 all raised to a power? That really needs substitution itself. So there's a much cleaner way to do it. Is whenever you can, let u be the whole complete stuff. Here's what I mean. If I let u be not just the tangent of x, but the tangent of x plus 3, all the stuff inside that parentheses, then when I take the derivative, it still works, because the derivative of tangent of x plus 3 is still secant squared of x, and the plus 3, its derivative is 0, so it goes away. But I want to let u be the whole stuff inside the parentheses, because that's exactly what I would do when I do the chain rule. I'd have the whole stuff inside the parentheses, and I'd multiply by its derivative outside. So what do I do from here? Well, I can just replace that stuff inside the parentheses, the tangent of x plus 3, with u, so I'll have a u to the 4th. The secant squared x and the dx, that's exactly my du. There's no having to solve for that equation or anything. It's already solved and ready to go. The secant squared x and the dx I can replace with du, and now I have just an integral of u to the 4th du, which is perfect, right? That's super easy to do. I just add 1 to the 4, the exponent, and make that u to the 5th over 5, right? Plus my c, of course, because I've integrated now. And then turn those u's back into x's. So that makes 1/5, and then a big parentheses with tangent of x plus 3 raised to the 5th power plus c. Okay, let's try a slightly more sophisticated example with one more wrinkle to it. Let's do this one. So now all that's changed here is before where I had tangent of x and secant squared of x, now I have tangent of 3x and secant squared of 3x. And those still match, so this is still going to work. Because if I look at this, I would go, yeah, big ugly parentheses raised to the 4th power. And the stuff inside the big parentheses, well, it looks like my stuff, and maybe what's sitting out beside it is its derivative, so that like it's been chain ruled. And sure enough, it has, or it's close, because the derivative of my tangent of 3x plus 3 would be secant squared of 3x, but then I'll get an extra 3 from doing the chain rule here. And there is no 3, but that's okay, I can fix that. So, here's what we'll do. We'll let u be the stuff inside the parentheses. Now when I take the derivative of my u, I'll get secant squared of 3x times an extra 3 because of the chain rule here, and then the dx. So what I can do is solve for secant squared of 3x and dx, and that will be 1/3 du. In other words, take that extra 3 over to the other side. And now, when I substitute all this back in, I get my stuff, right, my u raised to the 4th power. The secant squared of 3x and the dx all becomes 1/3 du. Okay? So that 1/3, I can pull it out in front. And how do you integrate a u to the 4th? Again, it'll be u to the 5th over 5. Okay? And if I wanted to do a little arithmetic when I need to substitute back in for x's and do a little arithmetic here and take that 1/3 times the 1/5. Again, that's not critical, but you may as well make that 1 over 15, because 3 times 5 is 15. And then I'll have, instead of u to the 5th, I'll have the whole stuff to the 5th, because u was my original stuff. So I'll have tangent of 3x plus 3, all raised to the 5th power, and again, plus c. Okay. Here's another one. This is a great example. This is an excellent example of the kind of integral that you'll see a lot in Calculus 2 and have to be able to integrate these kind of quickly. So, you look at this and you go, yeah, not really sure where any stuff is, right? So start playing with this in your head. So if I let u be the x that's in the numerator, the x in the top, its derivative would be dx. There's a dx. But then what do I do with all that stuff in the denominator? That doesn't really work. What if I let u be the denominator, all that stuff in the bottom? Its derivative would be, well, the 1 would go to 0, and the x squared would go to 2x. Oh, and look, there is an x sitting there, right? There is an x in the top. That x in the top I could use to make a du. So let's try it. Let's let u be all that stuff in the bottom. The derivative of that will be, the du will be 2x dx. Okay? And so then I can solve for the x and the dx, and gives me 1/2 of a du. So now, instead of having x over 1 plus x squared, the 1 plus x squared becomes my u, so that's my stuff. And the x and the dx becomes 1/2 a du. Okay? So what I've done is turn this all into a 1 over u kind of problem. Now, the reason that you might think to do this, of course, is that you know how to integrate 1 over u. So you want to start looking for something you can integrate, even if it has stuff inside of it. So in other words, I know how to integrate 1 over stuff. Right? That should be log of absolute value of the stuff. Right? Again, if the stuff were dealt with substitution, so that I have a du there, right? It all just works out. I've got whatever derivative of the stuff I have in order to make the substitution work. So the 1/2, I can still put that out front, leave it there, it's not a problem. When I integrate the 1 over u, I get log of absolute value of u. And since I've integrated, now I have the plus c. And so the final step is to go back and substitute in the 1 plus x squared in there where the u was. Now, technically, if you didn't put the absolute values in that last step, right, you could probably get away with it, right? But if I were you and I were doing this on an exam, I would definitely leave the absolute values there. The reason is you want to make sure that your teacher knows that you knew there's supposed to be absolute values there. Now, why do I say that you don't need absolute values in that very last step? Well, look at it really close. I'm taking the absolute value of 1 plus x squared. X squared is always bigger than or equal to 0. When you add 1 to it, what you get inside that log is always bigger than or equal to 1. So it's never negative. So you don't really need the absolute values because what you're taking the absolute value of is never negative. But that's only in this special example, right? Normally you don't have that problem. So it's much better to always leave the absolute values there, even if you don't need them, if only to show your teacher that you knew what you were doing. Okay, so here's a problem that looks similar, right? But it's not quite the same. Okay? So yeah, let's start looking at this and going, well, it doesn't fit any rule that I know, right? It's not an obvious like secant squared that I can just integrate and make it tangent, or it's not just 1 over x that I can integrate and make a log. It's kind of a mess. So can I take something and find its derivative somewhere? And you might think, I'll play the same game I did before. I'll let u be all the stuff in the bottom. So then I can make this into a 1 over u, and I'll get a log, and we'll be good to go. Except that, what's the derivative of all that stuff in the bottom? Well, the 1 will go away. The derivative of e to the 2x is, oh, here's a problem. E to the 2x times 2. Now, the 2 is not a problem on the outside that I'm multiplying by, but it's the 2 that's inside the exponent. Because what I have up there on the numerator is an e to the x, but not an e to the 2x. Does everybody see that? So if you're not sure why that doesn't work, stop and write out all the details and make sure before you go on that you realize that letting u equal the whole denominator can't work here, because the derivative of the bottom would be e to the 2x dx. And I don't have an e to the 2x. I just have an e to the x. And I can't make that 2 appear in the exponent. What I can do, though, is a little bit of algebraic trickery. And let's take that e to the 2x in the denominator and rewrite it as e to the x parentheses squared. And again, you see, laws of exponents means that's the same thing. If you have e to the x in parentheses squared, you have powers raised to powers, so you multiply the exponents. So that would be the same as e to the 2x. Okay? Now, written this way, right, this starts to look familiar. And this is yet another of the million reasons why you have to know your derivative and integral rules absolutely cold. Because we know that 1 over 1 plus, say, u squared du is just going to give us inverse tangent of u when we integrate it. So this fits that pattern, right? In the denominator, I've got 1 plus stuff squared. So as long as I have the derivative of the stuff sitting beside it, I can make substitution work. And I do. I'll let u be that stuff, which is being squared. Again, how do I know to let u be e to the x? It's not the e to the x in the top of the fraction that I'm letting be u. It's the e to the x inside that parentheses that I'm going to let be u. So if u is e to the x, then of course du would be e to the x still, and dx. Now that e to the x that I get from the derivative, that's going to be taken care of or turn into that e to the x that's in the top of the fraction. Right? So the 1 plus e to the x squared in the denominator becomes 1 plus u squared. The e to the x and the dx that were in the top becomes my du. And then I've got 1 over 1 plus u squared to integrate. That gives me an inverse tangent of u plus c, of course, because I've integrated. And then the final step is to turn the u back into e to the x. Now, the first time you see this, right, it's a really good question. Why did you think to do it that way, right? How did you know to do the little trick with the parentheses and turning e to the 2x into e to the x parentheses squared, right? And what in the world would make you think that? Well, the answer is you have to know your derivative rules absolutely cold. I mean, just, to the point where when you see 1 plus stuff in the bottom of a fraction, that immediately looks like the derivative of inverse tangent, because you're so used to working with all those derivatives and all these integral rules that 1 over 1 plus stuff squared is something that you know really well, and you're used to looking for it, and you know that that'll integrate and give you an inverse tangent. So it's just familiarity with the rules is the only way to see through this puzzle of how to turn what to use as your u in order to be able to integrate it. Okay, here's one more slightly related problem. Yuck, this looks even worse, right? I mean, there's a lot of possibilities there of what to use for the u. Maybe the u should be the square root of t, but then its derivative would be 1 over 2 square root of t when you do the derivative and simplify a little bit. That actually would make sense. That would give you an e to the u in all those places and take care of the t that's the outside. But then I've got like e to the u over e to the u plus 1. I mean, it still doesn't get that might work, but it still doesn't get us all the way there. It doesn't give me something that's obvious that I can integrate. So what else might I do? Well, I might try letting the e to the square root of t in the top be my u. But then what do I do with the plus 1 in the bottom, right? So the right way to make this work, and the way to tell what the right way to do this is to start looking for the most complicated stuff, right? That's inside of another function or inside of parentheses. Let that be your u. Okay? So the ugliest stuff that I could have here, right, would be what's in that parentheses, the e to the square root of t plus 1. The stuff that's inside the parentheses in the denominator. If that were my u, the du would be, well, e to the square root of t, but then from the chain rule, I have to multiply by the derivative of the square root of t. And now I've simplified it here a little bit, because the square root of t, when I take its derivative, I would treat that as t to the 1/2, so I'd make that 1/2 t to the negative 1/2, but to simplify that a little bit, I think it's a lot cleaner to make that t to the negative 1/2 be a square root in the denominator to bring that down. Okay? So again, this is just one little step of algebra and taking the derivative. But the reason for doing that is I've got a square root of t in my original problem there in the denominator. So all I have to do is take that 2 that's in the denominator there over to the other side, solve for e to the square root of t over square root of t dt. And that leaves me with 2 du. And again, if you remember to that example we did where I showed you the Cal 2 slides, what I would do there is put a 2 in the denominator next to that square root of t, and put a 2 on the outside in the numerator, so they would cancel each other and I wouldn't have changed the problem. But that leaves me then with a 2 times the integral of 1 over u du. Right? And so again, what would make me think that? It's because I know so well that I can integrate a 1 over a u, that when I see stuff in a denominator, I'm willing to let that be the u, be my stuff. as long as the derivative of that stuff is around it, then I end up with a 1 over u, and I'm good to go. Because when I integrate 1 over u, I get log of absolute value of u. So the final step, replace that u with the original stuff from the parentheses. So I get 2 log of absolute value of e to the square root of t plus 1. And then, of course, obviously we have to include the plus c.